Alright, this is chapter 14, section 1, and so we're going to talk a little bit about solids, liquids, and gases, just a little bit about that kind of stuff. So here we go. Alright, so first of all, kind of going back to what we talked about in physics, a little bit about kinetic energy. Remember that temperature is the study of, how fast the molecules are moving. And so we study the kinetic theory a little bit. And so the kinetic theory is the study of the molecules and how particles behave. So all comes together. And so the kinetic theory has three main assumptions. One is that all matter is composed of small particles. That's the first thing. And these small particles can be atoms, molecules, and ions. The second assumption is that these particles are in constant random motion. So basically meaning that they're always moving, which makes sense. Things have to keep moving. If they were not moving, then we'd be in trouble. And the third thing is that these particles are colliding with each other and the walls of their container. Okay, so that's the third thing. So, thermal energy is the total energy of all the particles within these molecules themselves. So, we talk about that the kinetic energy is, the vibrations and the movements within the particles themselves, and the potential energy results from the forces holding the particles together. And so we have to think, though, remember that particles are held together by bonds, and so remember that you have to think about that these particles are just basically vibrating in place, moving back and forth, back and forth. So the energy that we get is from these particular particles. We talked about temperature back in physics, so this should be a definition that you're already used to. It's just, again, the average kinetic energy of all the particles, how fast they're moving. Frozen water obviously will move slower than water that's boiling. That's, obviously that makes sense. So, all molecules will have kinetic energy. It's just when we get to a point where we get to something called absolute zero, this is where we have 0 Kelvin. That's not okay, that's 0 Kelvin. That's when we get to the point at which we are getting the point where things stop moving. Okay, we have three basic phases of matter, and you've probably heard this before, so I'm going to go through it pretty fast. But of course, we want to focus on how things are arranged, because that has to do with how things are set up and how things react and how things are able to work in chemistry. So solids, of course, they are packed very tightly close together. They have a very specific geometric arrangement, meaning that if you kind of look at the picture down here, everything is very organized, very structured. It's very important that it has that arrangement. It gives the chemicals its specific chemical and physical properties because of this arrangement. So if a particular solid didn't have this arrangement, it wouldn't react in the way that it did. So solids are very important that they have this very organized, very packed structure, because if not, most of the chemicals that are solids wouldn't act in the way that they did. Okay, so of course, if we take and we add heat, thermal energy, to a particular solid, the particles would start to vibrate faster. They would start to collide with each other. So then, once they start colliding, they overcome the attractive forces, meaning they start to, of course, break bonds. So if you break bonds, of course, then they start to slip out of their ordered arrangement, okay? And so that means that then we start getting that solid to melt. So that's where we get into now the next state of matter once we start to do that. And we actually call that process, though, of melting point, where the solid begins to actually liquefy and slip out of that ordered arrangement. And that's actually the amount of energy that's required to change a substance from the solid phase to the liquid phase. And that specific amount of energy is called the heat of fusion. So the temperature at which it will liquefy is called the melting point, and the amount of energy required is called the heat of fusion. And then once you get to that point where you have enough energy, or you've put in that heat of fusion in order to get the solid starting to liquefy, so you've reached that melting point, we now have, of course, liquid, where they have, the particles, of course, now have more kinetic energy than in a solid, and so you have those particles have overcome that attraction forces, and so now they're not as organized. Okay, I want to make that point. They're not as organized as a solid. I mean, look at that. They're still not spread super far apart. They're still not, super jumbled up, but they're not as pretty as the solid was. We're able to flow. They're able to take the shape of their container. So those are kind of the big things. So they're able to move over each other. Then again, once we reach that point where we've heated it up or added enough energy to where we get, these molecules just jumbling all over the place, they're bouncing, going crazy, we now have the gas phase, of course. The gas phase, they've overcome pretty much all the attractive forces. They have no fixed volume. They have no fixed shape. They're spread far apart in the container. I always use the things with gases that they just don't like each other. And so now you have your gas phase. Here's kind of your phase change diagram. So you can kind of see what it's called when you go from one phase to another. You've got, starting down here, oops. Sorry, I hit the wrong button, as usual. Oops. Starting down here with a liquid, you've got liquid to a gas. If you're going from a liquid to a gas, we call that evaporation. You have to be careful. We'll talk about that, I believe, in a second, where if it involves heat or does not involve heat. Because you can, never mind. We'll just use the term evaporation. I get excited. Evaporation, and then if you're going back from gas to liquid, you got condensation. If we go from gas to solids, if you go from gas to solid, we call that sublimation. If you go from solid to gas, it's called sublimation. If you go over here from a solid to a liquid, solid directly to a liquid is melting. If you go from a liquid to a solid, it's freezing. Okay, so how does a liquid become a gas? We already kind of talked about this. The particles in the liquid are constantly moving. And so, some of the particles start to move faster and have more kinetic energy. And so you get them to enter that gas state. And we call that vaporization. Okay, and like I said, I kind of got ahead of myself. I got excited. Vaporization can happen two different ways. It can happen by evaporation, or it can happen by boiling. There's two different ways that vaporization can happen, where you can go from a liquid to a gas. And so kind of just distinguish between the two. Okay, evaporation, first of all, happens at the surface of the liquid. Okay? And it can happen at temperatures below the liquid's boiling point. So this can happen just sitting out at the room right now. So it doesn't have to get up to a particular boiling point. It just has to have enough kinetic energy to escape the attractive forces of the liquid. So it just has to have enough energy to no longer want to stay in that liquid phase. So it just has to have enough kinetic energy to no longer want to stay at that phase of a liquid. And so then it'll go into the gaseous phase. That's evaporation. What distinguishes that from boiling? Boiling has to happen at a specific temperature, and that temperature depends on the pressure of the particular environment that you're at. So the boiling of a liquid is the temperature at which the pressure of the vapor of the liquid is equal to the external pressure acting on the surface of the liquid. So boiling has to happen at a specific temperature at a specific pressure. So so we have boiling point has to happen is a specific temperature, and heat of vaporization is that particular amount of energy that you need to put in. So if you want to get something from a liquid to a gas, if you're putting in heat and you're getting it up to a specific temperature, we could call it boiling. If you're just sitting it out on a table and just saying, hey, I'm going to leave it here for a while and see if it goes away and goes up to a gas, that's called evaporation. Diffusion. Diffusion is where gas particles are moving so quickly and are so far apart they have to overcome attractive forces between them. I just kind of like to think of I think sometimes the definition of diffusion is just kind of crazy. Diffusion, you know what diffusion is. Something diffuses. You have like cologne, for example. You spray it. What happens? Eventually somebody smells it across the other side of the room, because what does it do? That gaseous cologne smell, diffuses to the other side of the room. The gas goes from one side of the room and mixes with the room air, and it gets to the other side of the room. It diffuses. Okay? Kind of a gross example, I guess, is the same thing with when somebody farts. It starts at one side of the room, and what happens? Eventually somebody smells it on the other side of the room. That's the process of diffusion. It mixes with the other gases and mixes in. It's the spreading of particles through a given volume, okay, until they are uniformly distributed. It's easy enough. You know what diffusion is. It's just you've never put a definition with it. Whenever we heat a particular type of liquid, we have a heating curve of that liquid. I've put on here the heating curve of water. There's particular parts within a heating curve in which the liquid does not change, because the heat that goes in is needed purely to break the bonds and not change the temperature. So notice on this particular graph, here and here, it's what we call plateaus. The plateau means that at that particular temperature, all the energy going in is needed to break the bonds and not just heat up the liquid. So at 0 and 100 for water, all the energy that we are putting in at those particular temperatures is needed to break bonds of the water molecules instead of heating up the particular liquid. And you can see that when you're heating up any particular type of liquid. Okay, the last kind of type of liquid that we kind of put off the side, we don't talk about it a whole lot, it's called plasma. Plasma is not your typical plasma like you think about your blood. Plasma is the forces produced by high energy collisions that basically are from like electrons that are given off. So things like the stars, the sun, lightning bolts, neon or fluorescent tubes give these, auroras, all those kinds of things are your plasma. So those are kind of our last category of matter that, again, we kind of have. We don't talk about a whole lot, but thermal expansion. Things that happen when you heat things up is that, and it's kind of common, I mean, this is real logical. What happens when you heat things up? They expand, and that's exactly what we're doing. We're putting a scientific definition with something. So if you heat stuff up, what happens? Thermal expansion. The size of an object increases when the temperature increases. I put an example here, a thermometer. You guys know that. Oops. A thermometer. So you are sick, you put the thermometer in your mouth, an old school thermometer, I guess, and what happens? The stuff goes up inside. Why? Because when you get sick, technically, the stuff inside reacts to that, okay? Same thing with contraction. When things get cold, what do? Contract. They pull back. The cracks in the sidewalk are a great example of that. In the summer, when it gets hot, that concrete, it gets bigger when it gets hot. But in the wintertime, when it gets cold, that concrete contracts, and so the cracks in the sidewalk are more noticeable. Because those particles are slowing down. Water is an awesome molecule. We get so excited by water because it has, you could do a whole study on water because water is just amazing. Water is one of those particles that it has special properties because of how it's set up. It has special positive and negative areas. So if you look at the drawing down below, you see that because oxygen, it gets this, what's called a partial negative charge. So the top, this oxygen here gets this own special partial negative charge. And the bottom part, because of where the hydrogens kind of are, it gets partial negative charge. So it kind of splits the water molecule in half, where it gets one half is partial positive, one part is partial negative. And because of that, it kind of makes itself, it's called a polar molecule. And it makes it so it has poles, kind of like a magnet. And so you think about like a magnet, if we kind of draw that, we get a positive end and a negative end. The molecule does. And so what happens is that it attracts, and that affects the regions of water, and so that's why it gives it all its cool properties, why it makes a teardrop shape, why it curves when you put it in glasses, why it conducts electricity, why it does all the things it does. Water is just such a cool thing. And so why is solid water, larger than liquid water? It's because that when the temperature drops, particles usually move closer to each other, and so those charges will be attracted to each other and line up so only positive and negative zones are near each other. And because water molecules orient themselves to charge, empty spaces occur. So because of those polar molecules, it's hard for the positive and negatives to line up. And so actually, when the positive and negatives of those polar molecules start to line up, there's actually, larger spaces in water than with liquid water. So it actually expands versus getting smaller. So it's because of that whole polar idea. Now, not all solids, liquids, and gases go through what's called normal phase changes. So they have a definite temperature in which they change from solids and liquids. Some solids merely soften and kind of gradually go into liquids. Some things go directly from solids to gases. Something that goes directly from a solid to kind of like a melty thing is called an amorphous solid. Coming from the Greek word... Here, I got it right here. Amorphous solid without form. It comes from the Greek word without form. It's really cool. I think I have it on the next slide here. Yes. An amorphous solid, an example of an amorphous solid is glass. You've all seen maybe glass melt at some point. You know that it doesn't go straight from a solid to a liquid. It just melts. And it's because of the structure. Glass has this chain-like structure, the way it's made up, it's particles. And so instead of being a typical solid where it's all pretty and stacked up like a typical solid, well, it's actually still organized. It's neatly stacked like a solid should be, but it's kind of jumbled. It's a neatly jumbled stack. It's I think about it this way. Your mom tells you to go clean your room, And so you clean it up, like you shove everything in your closet, so it looks really, really clean. But if you look really close, like open your closet or open your drawers, people would see that it's not very clean and organized. That's what glass is like. It looks clean, it looks organized, but it's not. So that is an amorphous solid. So it changes, it doesn't change very well. It just goes in from a solid to a liquid, kind of jumbly. All right, so that's the end.